This presentation is delivered by the Stanford Center for Professional Development.
I want to finish up something about experiment design, which actually relates to our next topic, which is geometrical optimization problems. So experiment design, you recall from last time, is you're going to make a number of measurements. And you have a palette of possible measurements you're allowed to take. That's V1 through VP, parameterize these things. And you're given a budget, for example, just a total number. You're just told, make 40 measurements out of this palette of 50 possible measurements. Which 40 would you take? And we talked about that last time. When you commit to a set of 40, which is actually nothing but a set of integers on M1 through MP that add up to 40, when you decide on your allocation, you'll be scored on a covariance matrix. That's your error covariance matrix. Now, that's obviously a vector optimization problem because one person's error covariance matrix could be very small in one direction, big in another, and then you could have the opposite. So that's kind of obvious. So the first thing is you have to scalarize. And the second is there is this issue. It's a smaller issue. It's the issue of a relaxation from an integer problem to a continuous problem. We talked about that last time. So the most common scalarization is de-optimal experiment design. So in de-optimal experiment design, you minimize the log determinant of the covariance matrix. So this is the covariance matrix. This is, of course, convex, clearly, in the lambdas here. And this corresponds geometrically to minimizing the volume of the corresponding confidence ellipsoid. So this is sort of like if you're doing a problem involving positive definite matrices where you want it small, log determinant or determinant is something like the least squares there. It's kind of like if you can't come up with and defend another measure, then you might as well just go with log volume or something like that. So it's something like least squares. Okay, so this is the de-optimal experiment design. Now, one of the things is when we start doing applications, it gets extremely interesting to do things like take a problem that comes up as an application. This is experiment design. This is de-optimal experiment design. And you actually work out a dual for this problem. But what's often the case is that a dual of a practical problem will actually turn out to have an interpretation which is another practical problem, and it can be one from a totally different field or something like that. After the fact, everything will make sense, but it will not be remotely obvious at first that the two things are connected. So in this case, a dual, which I'll work out shortly, is this. So these two are duals. And of course, what I mean by that in the loose sense, what I mean is that I transformed this slightly, formed a Lagrange dual, and then made a few more small transformations of that one. Maybe I solved over a scalar variable. I mean, we'll get to that. This is called, so these are duals in the loose sense. However, they are duals in the following sense. Any feasible point here provides a lower bound for this problem, period. Okay? There's an easy transformation. If you solve this problem, you can solve that one, and vice versa. There's zero duality gap here. Absolutely zero in this case because the weak form of Slater holds. Slater condition says you have to have a point that's strictly feasible. The strong form of Slater's condition holds here because I just take all the lambda i's to be 1 over p, okay? And then the strong form holds. But anyway, so there's zero duality gap between these. Now, this problem actually has a very simple interpretation. N log n is a constant, so you're maximizing log det w. Or if you like, you're minimizing log det, say, W inverse. That's the log of the volume with a constant constant multiplier of a half or something like that, and then also an additive constant. Within an additive constant and a factor of a half or something like that. That's the log of a volume of an ellipsoid, and this would be VK transpose W inverse, parentheses, inverse, VK less than 1. And this is the problem of computing the minimum volume ellipsoid that covers the points VK. Okay? So, I mean, this sort of, by the way, this problem comes up a lot as well. In fact, I'll mention a statistical application of this right off the bat. Actually, we'll get to some of that in the next lecture, so maybe I'll wait. So what this says, and you can work out what complementary slackness says. Complementary slackness says that if lambda is positive, that means you actually carry out an experiment of type, if lambda 3 is positive, it means you'll actually use V3. You'll actually do a positive number of those experiments. Then you must have 1 minus VK transpose W VK 0. That means VK is on the boundary of the smallest enclosing, the minimum volume enclosing ellipsoid. So the picture is this. It's a very simple one. We looked at this last time, but very briefly. You have something like 20 choices of experiments to carry out here. Okay? Now, these experiments are pretty much the same as these. I mean, there's a negative sign. That doesn't matter. But the vector v is smaller, and that corresponds to, twice these measurements are the same as these and have twice the signal-to-noise ratio. So it would be foolish to choose any of these, and indeed, none are chosen. Now, over here, all the weight is put on these two. And this sort of makes sense, because the only difference among these is the angle. And given the choice of measurements, you would take measurements that are, to the extent possible, orthogonal. Okay? So it's actually sort of chosen this point and this point, and it's actually put a weight of 0.5 on each of them, meaning that if you were given a budget of experiments, half should be here and half should be here. That's what it means. And it kind of makes sense. There'd be no reason to skew them, because they're they're 30 degrees apart or 35 degrees. I mean, they're as close as you're going to get to orthogonal. They're the most mutually. They have the largest angle, and so they give the most mutual information or whatever. Or not in the information theory sense, but they're maximally mutually informative if you take ones that have a high angle. So that's what these are. Now, the interesting thing is the dual has a perfect interpretation. You take these 20 points and you compute the minimum volume ellipsoid that covers them centered at 0, and that is, in fact, the one drawn here. And sure enough, it touches 2 points, these two here, and these two actually are going to be the ones you use in the experiment design. So that's another way to understand that in experiment design, you're choosing points that are far. By the way, it's not as simple, or it's not as simple as just choosing the points that are farthest. That would be a greedy scheme where you would choose the experiments that have the highest signal-to-noise ratio. That's not the case. Because in that case, if one sensor had a very high signal-noise ratio, you'd basically only take that one. You actually compute the minimum volume ellipsoid that covers these points, and then these give you the other ones that fill in other directions and so on. Okay, so that's that. And I think I'll skip the derivation of the dual, other than just to mention a few things about it. It should be straightforward for you now. It's not something. There's no way you could look at this and just say, "Oh, okay." But it's something that in a few minutes you should be able to trace through. It's quite straightforward. The only interesting thing here, I don't know if we've done enough problems on this or have gone over this enough, is actually when you have a matrix problem like this, you actually have to calculate the gradient of the log of determinant of inverse of a matrix. That's complicated. The gradient is a linear function on matrices. And you actually have to, don't just take, the formula is basically, it's minus x inverse. But you have to be very, very careful to understand what that means. That's actually covered in an appendix in the book. So I'd recommend reading that. In fact, let's add that to our list on, and I don't remember what appendixes is. Okay, so it's the one that covers, let's say, that. What does it mean, and so on and so forth. Okay. All right. So how do you form when you have when you reformulate it this way and you have a matrix constraint here? It's quite straightforward to introduce a Lagrange multiplier. Normally, it would be nu transpose times ax minus b. Here, it's a matrix equality. The transpose is an inner product. An inner product for matrices is in general, trace x transpose y. These are symmetric, so it's trace xy. So you write this as trace z times the matrix residual here. Okay? So that's the origin of that. Otherwise, everything else kind of works out the same. And I'll skip the details. Just to say the bigger picture is it's basically, for any problem you look at and have time to actually think about carefully, it's actually worth your while to work out the dual, because the dual often has a very interesting interpretation, give you some better idea about how it works and all that sort of stuff. Okay. We'll move on to our last sort of generic family of applications, and these are in geometry, so geometric problems. These come up actually all the time. And we'll start with some of the ones that are least obvious, the extremal volume ellipsoids. So we'll look at that. These are some of the most interesting and least obvious applications. In fact, it's least obvious what you can do in these cases. So the Lohner-John ellipsoid of a set C, which need not be convex, at all, is the minimum volume ellipsoid here that covers the set. Okay, so that's the definition of the Lohner-John ellipsoid. Actually, it's unique. We'll actually, and by formulating as a convex problem, we'll prove that right away. So here it is. We'll parameterize the ellipsoid as this is the inverse image of the unit ball under an affine mapping. Okay? And that's a parameterization. I should point out there's at least like 4 or 5 totally different parameterizations of an ellipsoid, right? You can write it as a quadratic form, the forward image of an affine mapping of the unit ball. You can write it as the sublevel set of a quadratic function. You can write it all sorts of different ways. Which of these methods you use to describe an ellipsoid, to parameterize an ellipsoid, is going to completely change the convexity properties. And so when you have different problems, you're going to have to choose one of these. So it's not like this, this will not work out if we parameterize, for example, it this way, x minus xc, set of x such that x minus xc transpose, say p inverse x minus xc is less than 1. That's another parameterization of ellipsoid. And the data structure to describe this ellipsoid is a center point, xc, and a positive definite matrix p. Okay? Now, it's easy to go back and forth between this and this. It's just linear algebra. Okay? It's easy. However, if you formulate the problem here, you will end up with a non-convex problem for the Lohner-John problem. Here, it's going to end up being convex. So you have to choose the right parameterization. It makes a great deal of difference which one you choose. So this is the inverse image of the unit ball under an affine mapping. It's an ellipsoid. And it's not hard to go from this to this. It's not a big deal. A transpose A is P or something. Now, in this problem here, it turns out you can assume without loss of generality that A is positive definite. And that's not at all hard to show. One is this. It's got to be non-singular. If A were singular here, then it would of course have a null space. And in fact, this would be this could be called a generalized ellipsoid or a cylinder, because it would have an infinite. Anything in the null space, it would have an infinite dimension here. That's what this. It would have a direction along which it was infinite. It wouldn't be bounded in that case. Nothing wrong with that, by the way. Sometimes that comes up. That corresponds to A being positive semi-definite, not positive definite. Okay. Now the question is, why can we assume A to be positive definite? So anyone have any suggestions about why? If someone gave you an A here that was that is not symmetric, not positive definite, how can I compute this? How could I determine the same ellipsoid with an A that is symmetric and positive definite? How do you do it?
You just flip the sign of the eigenvalue?
You could flip the sign of the eigenvalues. A might not even be symmetric, but you're on the right track. What would you do? So let's write the SVD of A. Let's write A here as U sigma V transpose times V plus B. This is less than 1. Right? So this is the set of V for which this is true, right? And I need a suggestion. This is A. And I want to write this in a new form where sort of the new A and the new B are symmetric. A is symmetric positive definite. So here I'll write the skeleton. So I need a suggestion.
Just choose USB.
What's that?
Choose USB.
Okay, so you're going to choose what?
U equals V.
Okay. Choose U equals V. Yeah, I mean, that's kind of what we want to do, but you can't say that. I mean, somebody just gave us this description with A and B. Their A is not symmetric. So we don't have the right to say choose U equals V. They said, no, 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 this is the A I'm giving you. So one thing you can do is this. This is a vector, and if I multiply that on the left by any orthogonal matrix, it doesn't change the norm. That's the same. So I could multiply, let's just do this in our heads. Let's multiply this vector on the left by first U transpose, and then by V. And because I was multiplying by matrices, the first was whatever, so we're going to write it this way. V, U transpose, times U sigma phi transpose V plus B. Everybody cool with that? I mean, that's identical, because this is equal to that, because that's an orthogonal matrix. Everybody cool with that? Okay, and what do you have now? Now we're done.
You have V.
Yep, now you have this, and then everything's cool. It's V sigma V transpose plus, and then something here, which is V U transpose B. Yeah, I did. Yeah, somewhere. We're here?
Yep.
There we go. Thank you. Okay. Okay. And I'm going to call this A tilde, and I'm going to call that B tilde. And I'm done. Because I just took the original ellipsoid. I mean, this would be the code you'd write at the top of something, where you decide, it's decided in a group of people doing whatever development, that the data structure is the inverse of an ellipsoid is the inverse image of an affine mapping. Okay? However, you don't put in the specifications that the matrix should be positive definite. Okay? Somebody passes in this, but for your method, you need this. This is the stuff you write at the top that translates it to an equivalent one with positive definite A. Okay. Everybody okay on this?
Here could have negative entries, right?
No, it's a singular value decomposition. It's not an eigenvalue decomposition. Singular value decomposition, and it's non-singular, the original matrix A, so they're all positive, so we're cool.
Oh, so that is the assumption that if A is non-singular, then A tilde is non-singular. If A is singular.
Oh, pardon me. Right. A is square and non-singular, and therefore U and V are square they're orthogonal matrices.
But the whole point of this is that A was not square.
No, no, no. The whole A is square. The question, actually, you can do this, by the way, if A is not square too. But you'd have to. You can do this in that case too. What A has to be in that case is, well, let's see. It has to be what, fat and full rank, or skinny. Maybe fat and full rank, I think is what it has to be. Sorry, skinny and full rank is the most general. If you want to allow people to describe an ellipsoid this way, in the most general way, A, I believe, can be skinny and full rank. That'll do the trick. Yeah, exactly. So in that case, we're cool because, and then everything I did here was kosher. So let's just, in that case, you have to go back and check that U has the rights. Well, I guess U transpose U is always cool. Right. So, okay. So, question?
Why did we embark on this journey in the first place?
Well, I haven't said yet.
Not the journey of the ellipsoid, the journey of positive symmetrizing the matrix.
Well, now, would we embark on a journey? We shouldn't answer that. No, I was going to say, would we embark on a journey that was unneeded? The answer is yes, we do that every day. But they're kind of weird things. I don't usually have it in writing, those weird little journeys and side trips. So obviously, this is going to come up, right? Indeed, it will, in 2 lines. So, but thank you for posting the sign there, which is, why are we doing this? Okay, so let's move on.
But why does A have to be, so you're assuming A is non-singular?
That's right. Oh, why? If A is singular, this doesn't describe an ellipsoid. It describes something called a generalized ellipsoid. It's called a cylinder, in fact, because it can have it will be infinite in some directions. In fact, specifically in the null space of A. Along the null space, any point in the null space of A can get infinitely big and satisfy this, and everything's cool, right? So in that case, so that's not an ellipsoid. By the way, such a thing has infinite volume, and if we're minimizing volume, it's not going to be it's sort of infinitely bad. It's not going to be of interest. So that's how that's why. Okay. Now I'm going to use this parameterization, and yes, I wanted a symmetric positive definite for a reason, and now you know why. Here it is. By the way, you see this problem here? This problem is actually correctly the Lohner-John ellipsoid problem, even when A is not symmetric. Okay? It is, because I assure you, log det A is going to be the volume. It's going to be the volume, well, multiplied times the volume of the unit ball in that space. If that's going to be the log of the volume, actually, sorry, added to that, of this ellipsoid, period. Okay, or 1 over it is. All right, so, however, the log of the determinant of some non-symmetric matrix is some insane function that is not, in general, convex. In fact, it's never convex. Okay? Just not. So, however, if I assume A is symmetric positive definite, then this problem here is convex, and that means we can solve it. So that's it. So here I minimize log det A inverse. And you have to check about the volume and things like that. But, I mean, that does transform. The volume transforms by the factor det A inverse here. And now, to say that, I mean, I can rewrite this way. I don't have to write it this way. I can write this, right, for all V in C. This just basically says that for every point in C, you're in the ellipsoid. You're in the ellipsoid if and only if AV plus B, when you take the norm, is less than 1. To say that the ellipsoid covers C is to say that for any point in C, norm AV plus B is less than or equal to 1. So that's this statement. Now, by the way, we know immediately this is a convex problem. Some people, by the way, would call this they'd glorify it and make it very complicated and call this a semi-infinite problem. Why? Because that is a convex constraint. In fact, it's a 2-norm constraint on the variables. Now, by the way, the variables here are A and B. So actually reading this kind of stuff requires serious concentration because it's a very standard convention that symbols like A and B and C and alpha and beta are parameters. And variables are things at the end of the alphabet, like U, V, W, X, Y. So this is totally turned around. And the variables are A and B. And the parameters, well, V is a dummy parameter, okay, but nevertheless. Okay, so you have to read this correctly. That is a 2-norm constraint. It's nothing more. But it's 1 for every point in C. Oh, if C is infinite, this is a so-called semi-infinite problem. Okay. Now, you may not be able to have a tractable representation of this semi-infinite constraint. In some cases, you can. I mean, 1 is a finite set. So here, I give you a bunch of points, and you have to calculate the minimum volume ellipsoid that covers them. Now, in this case, it's easy to say this because you just write that. This is a convex problem. So now you know something. And of course, it's not just the Lohner-John ellipsoid for the set consisting of these points, but in fact the convex hull of those points, and that's a polyhedron described by vertices. So you just learned something which is by no means obvious, and that is that if someone gives you a polyhedron defined by its vertices, then computing the minimum volume ellipsoid that covers those points is a completely tractable problem. Okay? Everybody got that? And in case you think, you know, sort of this is obvious and everything works and all that, watch out. Because if I give you a bunch of points like this, and I give you a polyhedron described by the vertices, and I ask you, for example, to solve a variation on this, which is please compute the maximum volume ellipsoid that fits inside it, that's actually NP hard. Okay? So, I know I'll show you, of course, I'll focus on the ones that actually we can do. But watch out. One step off this path, and things get very complicated. And these are not obvious facts. They're just not obvious, period. Okay? Let me mention a couple of things about this one. This has huge applications, sort of choosing maximum volume ellipsoid around some points. And let me sort of just give you one or two. They're beautiful applications. Here's a really very nice one. Suppose you just simply have V1 up to V, it doesn't really matter, 10,000. It doesn't matter. These are measurements they're vector measurements. They're in R10. That's it. They're vector measurements. And what you want to do now is check, are there any measurements that like stand way out? In other words, are there outliers? That's the question here. Are there some measurements here that are big and somehow don't fit with the set? Okay? So how would you solve a problem like that? It's vague. Comes up all the time. I want to identify outliers in a bunch of samples. What would I do? Make some suggestions, actually. Let's start with unsophisticated ones. So what would be the first thing you might do? Sure. Yeah, absolutely. So the simplest thing is let's subtract the mean of these from here. So now they're sort of centered roughly around 0. That would be reasonable. Then, actually at that point, you might just look at the norms of all these things. And if all the norms were on the order of, half, 1, 2, and a handful of them have a norm of 50, then there's your outlier problem solved, right? So basically you have a cloud of points like this and a couple just way out there. Okay. Everybody agree? So that'd be the first thing you might do. Then you might say, well, no, that's not right. What I'll do is I'll take these points, I'll subtract the mean, that will center them, and now I'll calculate the empirical covariance matrix of them. That gives you it gives you the ellipsoid that kind of covers the cloud the best. Everybody cool on that? Then I might even change coordinates so that ellipsoid was was uniform, was a ball. That's a very hard change of coordinates, the one I mentioned before. I don't recommend it without a lot of practice. So you change coordinates so the ellipsoid becomes a ball. Came out right. And now it means, roughly speaking, the data kind of varies equally. Now, if you start seeing points that are way out, these could be your outliers. Everybody okay on that? Now, the problem with that is that one, that would actually work. That would probably work okay. Turns out a much more sophisticated method than that is actually to compute the minimum volume ellipsoid that covers these. Okay? The points that are on the surface of that ellipsoid actually are ones which you would declare as candidates for outliers. Okay? And in fact, the way this often works is you take those points and you remove them. And then you redo whatever you were doing, some least squares problem, some singular value decomposition, PCA. It really doesn't matter. You do the processing. What you're looking for is something like this. You want to remove a small number of points, do whatever signal processing or statistics you were doing before, and have the answer all of a sudden get way better. Right? So you want to remove 8 points from a set of 10,000, do some signal processing, and all of a sudden have like an excellent fit. This is a hint that at least that those 8 included the ones that were messing you up before. Everybody see what I'm saying? That would be outlier methods. Okay, so this is called, this is called in statistics, it's called ellipsoidal peeling. It's the greatest phrase, right? So you have a giant pile of data, you shrink it, you stick an ellipsoid around it, and you remove those points. So once you remove those points, by the way, if your quality of estimation or whatever signal processing or statistics you're doing didn't get like really good, you do it again. You've removed those points, and the ellipsoid shrinks down to fit the next one. And this is called ellipsoidal peeling, and you do this in waves or whatever until you like what you get, or until you have no data points anymore, in which case you went too far. So, yeah?
I was going to ask on that question. So like say you do it, you peel like 2 or 3 layers and you don't see any substantial change.
Yeah.
Does that tell you that maybe, you didn't have any terrible outliers before?
Yes, it might tell you that. Yeah. Generally, when that happens, when you do a couple of cycles of ellipsoidal peeling and it doesn't get better, generally you don't admit to people that you ever did that. So, yeah, you just go back and say, it's not working. That's what you do. Although, you're prepared if someone says, how do you know that there's not, maybe there's just like 5 or 6 outlier, just like bad data points that are completely messing up your, PCA or whatever you're doing, or your image reconstruction or whatever it is. That's how And then you'd say, well, I did some ellipsoidal peeling, and nothing got better. By the way, we've already talked about it last time. What's another method for dealing with outliers? I mean, just grossly. What? Yeah, you would go to an L1 type norm or a Huber norm, something like that. Huber's not a norm, but something, you'd go to a robust norm. But by the way, you could do the same thing there, the peeling thing. Okay.
How do you know which outliers to take out in each layer without doing it?
Take all of them out. You take all the ones that are on the boundary. If you don't want to take as many out, if there's 10,000 and these are in R10, I forget how many are going to be on the boundary, but it's generically something like 50. So 50 out of 10,000.
So you do the fitting problem, and then you
Right.
take away the boundary and do it again.
Yeah, so I do minimum volume ellipsoid. I think generically about 50, 55 or something like that will be on the boundary. By the way, if you take out the 55 and all of a sudden like your image appears and there's like somebody's head, you're doing medical imaging, and you go, then you know the following. You know that there were some outliers, number one, and number two, they were within the 55 you removed. Now, if you care, you can go back and start putting points in one at a time until the head goes away. Okay? And then you say, all right, so if you care, but on the other hand, if you have 10,000 measurements and you throw away 55, it would seem unusual if, so suppose instead of you threw away 22 outliers and whatever, 33 non-valid data points. Loss of 33 points, I mean, I'm just talking this is very hand-waving, but loss of 33 points out of 10,000, or I should say 9,950, it's not going to really make a big difference. So that's what you do. So you can add them back in or whatever you like. So yeah, these are fun. These are actually fun methods. They can be shockingly effective. And I should add, actually, on the whole issue of outlier detection, I should just make one comment about it. When an outlier is like totally off scale, anybody can do it. Okay, so if like you're getting a bunch of measurements, and a bunch of them are like 1, 2, 3, -5, -6, and all of a sudden one is like 1e plus 37. Okay, you don't need advanced methods to detect that as an outlier. That's because a bit flipped in a floating point representation or something, in the exponent. You don't need this for that. Okay. On the other hand, if the outliers, basically don't, if an outlier is just like, it's just off a little tiny bit, it's just some like 1/f noise, and it's not Gaussian, but it's not huge, it's not big enough to mess up your algorithm, or you have enough data that it gets averaged out nicely, then you don't have to remove it. But there's a band of situations right in the middle where being smart actually is going to pay off. And it's that band in the middle. So it's when if the outliers are small enough, well, they don't really hurt anybody. If they're big enough, anybody can spot outliers. But there's a pretty big band right in the middle where being smart is going to make the difference between successful signal processing statistics or whatever this is, whatever application it is, and not. So that's just my comment on this. I guess it's silly. That's the case for all problems have this band. Yes?
I don't see why we are looking for minimum volume ellipsoid containing all the measurements. It's just to remove outliers.
Yeah, so you're removing outliers. And so the argument would go, so first I'll tell you the truth. The truth is it's a heuristic. So it cannot be defended. However, you can say in its defense the following. If I simply removed the values of V with large norm, that would be something that is not scale invariant. If you were to rescale the data or transform the data, I would remove a different set because I could make a different set of points look big. Okay? The interesting thing is if you do minimum volume ellipsoid, that's actually affine invariant. You will select the same point. Because think about it. If you have a bunch of points and you transform them, like by any linear mapping, you wiggle them all around, and you recalculate the minimum volume ellipsoid, you get a commutative diagram. So the minimum volume ellipsoid that covers a set of points is affinely invariant. It commutes with an affine change of coordinates. Therefore, if someone says, why are you going through the trouble? Why not just take the norm and remove the ones with the largest norm? Right? You would say, I'm doing something a little bit more sophisticated. I'm minimizing the one that is large, but my measure of large doesn't depend on the coordinates used or the scaling used. It's more sophisticated. So, by the way, if you draw that story out long enough, people won't notice that it actually doesn't answer the question, which is why. It's merely a justification. So, okay. All right, so that's an application of this. This is sort of a dual problem. That's maximum volume inscribed ellipsoid. So here I have an ellipsoid. We'll get to this. Here we're going to describe the ellipsoid, by the way, as the forward image, not the backward image of. It's the forward image of a unit ball under an affine mapping. And again, I can assume, I won't go through the details, that B is positive definite here. Now the volume is proportional to det B, and the problem is to maximize log det B subject to this. And what this says is, there's another way to say this. It basically says that the sup over U, over the norm ball of BU plus D is in C. So that's another way to say it. Is if you want the semi-infinite representation, you would write BU plus D is in C for all norm U less than 1. Now we know, by the way, that is a convex constraint on B and D. Why? Because for each U in the unit ball, this is a convex constraint. And remember what the variables are here. It's B and D. This is not obvious. U is fixed. That's an affine expression. It's affine in B and D. Actually, it's linear in B and D, in fact. And so you have the constraint that a linear function should be in a set. Oh, sorry. This is the case if C is convex. Sorry. If C is convex, this is a convex constraint. Okay? Now, you still have to be able to evaluate this to make this interesting. And there's actually a very simple case when you can, and that is when this is, the simplest case is when this thing, when the set C is a polyhedron. Because I can easily calculate, I can tell you whether an ellipsoid described this way lies inside a half space. That's easy. And the way you see that, that's an easy calculation. We want to know, is it true that BU plus D, let's write a half space. So the half space is the set of X such that, let's say, F transpose X is less than G. Okay, that's our half space. And I want to know, is it true that BU plus D is in H for all U norm less than 1? That's the question. Okay? And the answer is easy. Yeah, we can calculate that. The question is whether F transpose BU plus D less than or equal to with a question mark, like that, for all U less than 1. Everyone agree? Now, by the way, we're focusing on this as a function of B and D. We're getting there. Now, the second term is this, F transpose D, and has nothing to do with U, like that. And here, I'm going to write this in a different way. I'm going to write this as B transpose F transpose U. And this should be true for all norm U less than 1. Now, if someone walks up to you and says, I mean, obviously, and you form an inner product with a vector and says, you know, I need the inner product of a vector with U. U ranges over the unit ball. We know exactly what these numbers range over. They range between plus minus the norm of B transpose F. Okay? In fact, to be quite precise, that's Cauchy-Schwarz order, but in the general case, general norm, it's plus minus the dual norm, the dual of that norm. So the maximum value this can have is this, period. And that is with the choice U equals B transpose F divided by norm B transpose F. That's the worst thing that can happen. So these are all if and only ifs. I haven't drawn them, but it's that. Okay? And then we have that. And that's it. We're done. Okay? Because now this is tractable. That is a convex function of B. This is a convex function of something happened there. D. Thank you. That's a linear function of D. The whole thing, this is clearly convex in B comma D. Okay? So that's the condition, and that's what we have here. Maybe I have it wrong here. Or did I assume B is symmetric? Yeah, sorry. I assume B is symmetric. So the transpose isn't needed here. Okay, so I get that. By the way, just let me point out, you're used to it. I don't know, we're 6 weeks into the class or something like that. It's not a big deal to look at that and say that's a convex problem in B and D. These are things that if you don't know this material, that looks like a hopelessly complicated problem. I mean, hopelessly complicated. Just because, it's got the log of the determinant and all that. You wouldn't know anything. This is non-differentiable. You know that. The norm, that's not norm squared. That's norm, right? But you look at that and you just say, well, that's a second order. That's a second order constraint. It's nothing. It's a second order cone constraint. So, all right. This allows you to calculate, to compute efficiently the following. This says that if you have a polyhedron described this time not by the vertices, but by the inequalities. So basically, you have these things, AI, like that. You can now calculate efficiently the maximum volume ellipsoid that sits inside it. Okay? And that you can do efficiently. Now, interestingly, if I take a polyhedron described by inequalities, and I ask you to calculate the minimum volume ellipsoid that goes outside, the minimum volume ellipsoid that covers it, that's NP hard again. So you have to watch out with these things. They're not, I'm just casually mentioning them here. This is not simple. Things that are, they're easy problems and just minor variations on them are very hard. Another question?
Is the NP hardness because you're using the representation of the polygon which doesn't actively constrain? Because like the
something like that. Yeah,
head.
NP hardness is actually easy, very easy to see. It turns out, you want to hear something that's NP hard? Is just the following. Forget finding the minimum volume ellipsoid that covers a polyhedron described by inequalities. Try this much easier problem. Suppose someone just asks you the following. Here is a specific ellipsoid. Can you please tell me if it covers my polyhedron? That's basically, is it even feasible? That's the feasibility. Sorry, that's not even the feasibility problem. That's not find a polyhedron that's feasible. It's basically check if a specific polyhedron is feasible. That's NP hard. Turns out it's maximizing a quadratic, convex quadratic function over an ellipsoid. And I can easily embed that to all sorts of NP hard problems. So, yeah, but I don't know that I really answered your question. I don't know that I really have a good answer for, why is it easy to go from if the data structure for your ellipsoid is the vertices, why is it easy to calculate the minimum volume in covering ellipsoid, but hard to calculate the maximum volume one inside? And why does it reverse here? I don't know. I don't really have a good story for that. So I don't know. The question?
So given this description, for example, you have this inequality description. Can you actually efficiently find the vertices?
Excellent question. Now, of course, if you could transform between these two data structures described a polyhedron, then of course, right here, right now, we would have shown P equals NP. Now that, I'm not ruling it out. Could happen someday, maybe around week 8 or something like that. No, no. So there, I'm glad you pointed that out because in fact, there's a catch there. So the question is, given a polyhedron described by inequalities, can you describe it by its vertices? And the other way around. And in fact, these are just two different data structures to describe a polyhedron, right? That's no problem. Now it's interesting because, for example, ellipsoids, we were just talking about multiple data structures to describe an ellipsoid. Those are all equivalent. They're all about the same size. They all involve like some kind of a matrix. And they involve a vector, roughly, and that, transforming from any one to any other is just linear algebra. That's all very straightforward. Everything is polynomial. It's all like n cubed or whatever, right? So those are sort of equivalent. They're different but equivalent parameters, polynomially equivalent parameterizations. Now, in general, there's some pretty shocking things. I'll just mention some of them. If you have a polyhedron described by inequalities, it is possible to list the vertices. It's possible. There's algorithms that just work, that list them. Here's the problem. The number of vertices is exponential in the problem size. Okay? So even, you know, if you have I mean, things you can just write down in a minute. You could just write down, for example, take 100 dimensions, 200 linear inequalities. Okay? So that's nothing, right? You can solve an LP of that size. Well, in 3 weeks, you'll write a code for it. But the point is, that can be solved literally in milliseconds. Okay? So, I mean, we all, you know, everyone has the right visualization skills. When I say minimize C transpose X subject to AX less than B, where A is 200 by 100, we're all visualizing the same thing. We're visualizing an ellipsoid, sorry, a polyhedron and a direction, and you kind of find the vertex or whatever that's most in that direction. Everybody got that? Now, here's the problem. The number of vertices of a polyhedron in R100 with defined by 200 linear inequalities is absolutely immense. I mean, it's some number that's, you know, it's on the order of like 100 factorial or something like that. I don't know what it is. But, and by the way, if I'm not quite right, and that's not equal approximately to the number of subatomic particles in the universe, I have to change those numbers very slightly, and it will be. Trust me. Okay? So, yeah, so that's the problem, is that going from from inequalities to vertices can lead to a huge increase in the size of the problem. That's the first problem. Now, by the way, for certain cases, it's not. I mean, if everything's in R2, anybody can figure out a way to transform between these two representations, vertex versus face. Well, in that case, edge. Anybody can do it. In R3 as well. And if you go to Google and type things like, you know, transform, vertex, face, blah, 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 you'll find tons of papers, but it'll be for specific cases like R2 and R3 is what you're going to find. You'll even find, for example, in some RKs that there'll be polynomial algorithm, but K has to be fixed, the dimension. So you'll even see that. By the way, the other way has the same problem, going from one to the other. So anyway, let me summarize all this because it was a weird random walk. So let me summarize it. The change in data structure to describe the different parameterizations of ellipsoids, that's casual. It's linear algebra. It's just linear algebra. It's taken some square roots, a couple of singular values, inverses, nothing. Okay? Changing the data structure to describe a polyhedron from vertex to inequality description, that's not casual. So that's a very important thing to know. I mean, unless you're in R2. But in R2, it doesn't seem to me there are any real problems anyway, because your eyeball can solve all of them, and it hardly matters. Okay? So I didn't even consider those to be real problems.
How is the problem we just solved earlier before we got to this example not correlate with what you're just saying about covering the outer, finding the minimum?
In the problem before, you're given the vertices, and you're asked to find the minimum one. That's easy. In this problem, you're given the faces, and you're asked to calculate the maximum volume ellipsoid that sits inside it. Those two are the easy problems. You flip those two, or rematch them, and they're actually essentially infinitely hard. Not only are they infinitely hard, but they're basically, you don't even get to this point. Just if someone just alleges an ellipsoid covers a polyhedron, you can't even verify it. You wouldn't know, let alone optimize over such ellipsoids. So there's I mean, these are subtle, and you have to look at them carefully. Think about them. Okay, now there's an amazing fact here, and it's actually beautiful. It's a sort of a fact about geometry. It's just absolutely beautiful, and it's this. Take a convex bounded non-empty interior set and compute the Lohner-John ellipsoid. So that might be, say, this polyhedron here, and you compute the Lohner-John ellipsoid, so you find the minimum volume ellipsoid that covers it. Okay, and that's this one. The following is a fact, comes right out of duality. I won't derive it, the derivation's in the book, comes right out of duality. If you take that ellipsoid and you shrink it by a factor of n, then you're guaranteed to be inside the set. Okay? By the way, the same is true here. If you take the maximum volume ellipsoid that fits in a set and you grow it by n, it covers the set. Okay? Now, you might say n is a big factor. Well, yeah, but at least it's a factor. And it basically says the following. By the way, if you split the difference, I can say it this way. I can approximate any convex set bounded, non-empty interior, that kind of stuff. Any convex set in Rn within square root n. That's what it means. Because I would split the difference here, right? I'd puff up, I'd shrink this ellipsoid by square root n. And then I get one where if you scale it by square root n, you cover. If you shrink it by square root n, you're inside. Okay? By the way, if this set is also symmetric, you can sharpen this to square root n, in which case I could even say I can get an n to the 1/4 approximation. The importance of this is extreme, both theoretically and practically. And let me say why. This basically says that ellipsoids are universal geometric approximators of convex sets. That's what it says. Because I can bound I can get a bound and there's a fixed factor whereby I can shrink and expand and fit inside and outside the set. Everybody got that? Now, that's going to come up. It's going to have lots of implications. But what about this? What if someone says, how about, a ball? Well, a ball doesn't have that property, obviously. Because, for example, here's a convex set. I can make it as skinny as I like, but sort of the minimum size ball that fits this is quite big. And the minimum size ball is like that, and there's no bound on these. So I could hardly say that I cannot approximate a convex set in Rn by a ball. How about a bounding box? How about a rectangle? Can I do it by a rectangle? The answer there is n. That's got n parameters. Ball only has it's got n. A bounding box has like 2 or 3n or something like that. That's not enough either. Because in this case, for example, the bounding box can look like that, the biggest one, that's the bounding box, the smallest box that covers the set. The biggest box that fits inside is going to be tiny, period. And there's going to be no bound on the ratio. So ellipsoid is sort of the first time when you get enough sort of free degrees of freedom to carry out universal approximation of a convex set. And let me just ask you another one just for fun. How about simplexes? That's the convex hull of n plus 1 points. By the way, answer's not obvious here, so you're just going to have to guess. But I say you can do it. So how about simplexes? What do you think? Can you approximate any convex set by simplex? What do you think? You can. Yeah, you can. There's enough. You have enough free parameters in a simplex to do that, and it's easy because you approximate it by an ellipsoid, transform the ellipsoid to the unit ball or something like that, and then stick a simplex around that, and you can even bound the ratio and all that. It won't be n; it'll be n squared or something. Doesn't matter. It'll be something. It'll be bounded. Question?
In this case, you use a rectangle instead of.
Oh, you mean a rectangle that can rotate? Yeah, then you can do it. Right. Then you can do it. Of course, we don't know how to calculate such a thing, but if you could do it, that gives you enough degrees of freedom to cover it. Okay, so ellipsoids are not just sort of convenient things that describe shapes of things. It's actually very worthwhile to understand and remember that there's a sense in which they capture sort of something like the first order approximation of any convex set is an ellipsoid. By the way, let me mention one more property of this. Suppose you took, let's say, EE 263. Let's just suppose you did. Okay, and someone says, what are you doing? Or you take a control class, or for that matter, you take a statistics class. And someone says, what'd you do all quarter? Everything you did involved quadratic norms, right? You'd have quadratic functions. In control, you'd have x transpose qx. In statistics, it would be hidden by something else or whatever. And someone would then ask a question like, they'd say, what'd you learn 260? Well, I could minimize a norm. And they'd say, a 2 norm, really? And then they'd say, does the sum of the squares actually come up in your problem? Is that really what's important in your helicopter design? And you could look at them, see how gullible they are. And if they look gullible, you could try to go for it and go, oh yeah, absolutely. Yep, sum of the squares of the vertical acceleration, pitch rate, absolutely. That can't be more than 1.3. If they go for it, the conversation is over. If they don't go for it, then you'd say, all right, I'll tell you the truth. No, we don't care about sums of squares of things. It's just because we can do it, and because that's the only class I took so far. So that's generally the truth about least squares. Okay, so all right, how does that have to do with this? Well, let's suppose that there is something you really care about, like maneuverability or ride comfort or something. It doesn't really matter. And suppose what you do now is you go around and you run huge tests, wind tunnel tests. You have pilots write things out and say whether they like the ride or not. And anyway, you end up with some weird set that looks like, you know, some kind of weird convex set that looks like that. That's like nothing's happening. And this is sort of the set of ones judged by, you know, wind tunnel simulations, actually getting pilots to ride it and all that. And they all say this is okay. If you're, this is of course in a multidimensional space, but you know. And if you're in that set, you know, one of these things is like pitch rate, one's this, one's the RMS, when it doesn't matter. If you're in that set, everything's cool. That's it, okay? And that's the real set. And this is not an ellipsoid. Let me tell you, it is not an ellipsoid, period. That's the real, this is the set. Okay. Now, this actually, now, what you know now allows you to do something that would let you sort of go back and in a posterior way justify 263 material. For that matter, you could go back and justify ordinary regression. And here's how you do it. In fact, somebody suggested. So that's actually the set of acceptable ride qualities, as judged by horrible long simulations, questionnaires with pilots, and blah, 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 and whatever. So, all right, this is where people like threw up and stuff over here. Okay, so this is where they crashed, actually. This is where they threw up. But anyway, so what do you do next? Precisely. You just make an ellipsoidal approximation. Probably in this case, you might want to make this one. Again, it's, you know, there's different. You might want to make the inscribed ellipsoid. Then you take this and you go back to the intern who has only taken 263 and you say, this is the norm you're going to use. And they, yeah, it's a stupid 6x6 matrix or 8x8 matrix with a bunch of entries. And they go, where did all those come from? And you say, last year's intern, right? It was a lot of work to get it. But you see my point here? That you can actually do, but by the way, the ideas I'm talking about, as far as I know, like no one actually uses them in practice, but everyone should use these ideas in practice, right? I mean, this just comes up everywhere. I mean, if you're in control, a lot of the methods actually fielded involve quadratic forms like Q and R and this, and then you ask, like, the truth is, where do they come from? People make them up. They don't have to be made up. They can be, you can actually do something intelligent and actually get things that do shape the way you really, that do actually capture, not exactly, obviously not exactly, but crudely, they capture the shape of the set. By the way, over here, this efficiency, which is a factor of n, that's something that only matters to a theorist. Okay? And by the way, can anyone guess what's the worst set to ellipsoidally approximate? Just in R2.
Something like a
Oh no, let's first talk, let's talk about ellipsoidal approximations in R1. That's a short conversation. How does it go? How well can you approximate a convex set in R1 by an ellipsoid in R1? Oh, very well, because they're both intervals. Okay, so that was the n equals 1. Let's do n equals 2. Well, you know it's it can never be worse than 2. Can it be as bad as 2? A factor of 2, that's the theory says 2. And the answer is sure. A simplex is like the absolute worst thing you could be asked to approximate, because in that case your outer ellipsoid looks like that, your inner one looks like that, and they're 2 to 1, that's n, and that's general. So this n here cannot be made better. Now a simplex is kind of a weird, sick thing. It's got all sorts of corners. You know, it's got corners on it. In fact, it's as sort of, it's as pointy as a convex set can be, roughly. Okay. Now, what do you imagine? A lot of convex sets that come up in practice, the approximation number is definitely not n. It's often much, much less. I mean, for example, if we actually went out and worked out ride qualities or things like that for a vehicle or anything like that, you would find most sets that arise through natural causes. What I'm about to say is, of course, just total hand waving, but I believe it to be the case. Well, Actually, since I'm not making a statement, it cannot be disproved. So, however, as a rough idea, we'll say this. Most of the convex sets that come up through natural causes can actually be approximated by ellipsoids stunningly well. Nothing close to n. Okay, so I just mentioned that. That's to those of you who are worried about that factor of n. You needn't be. Okay, so that's our discussion of that. Centering, that's an interesting problem. So in centering, it works like this. You have a set, and you want to find a point that's deep inside the set. Now, by the way, we've already seen one application of this, which is design centering, so which is yield maximization. So in yield maximization, this set describes the set of acceptable values. In other words, then the point that you're looking for is what you tell people to shoot for and manufacture. That's what you want to do. I mean, you can also think of less socially positive applications. This could be the range of points where if you're within there, you take out a target, and then you want to ask somebody where do you put your sight, right? And that's another question. And the answer is you don't put it there, and you put it right in the center. What center? You want to maximize the probability there that you're in this set. But we'll go back to manufacturing. Okay, so here. Now the simplest, actually the yield centering, we already talked about that. That's actually a convex problem provided the probability distribution is log concave. Doesn't mean you can solve it. You can, but not by methods from this quarter. But you can solve it. It's at least abstractly, it's a convex problem. So a lot of people use various heuristics for that work unbelievably well. One is this: you find the center of the largest ball that fits inside the set. Depending on what the set is, if it's a polyhedron, for example, we already looked at that like day one for linear programming. This is a linear program to calculate the maximum volume. Sorry, well, it is the maximum volume, but it's the largest ball that fits inside a polyhedron. That's an LP. By the way, I can say largest because you would only say largest ball if this were, you'd only use the word largest if there were linear or total ordering. But for balls, there is, because you can, at least if you're talking about the size of a ball, it's the radius, and so they're totally ordered. You would never say what's the largest ellipsoid inside a set, because that makes no sense. You have to put in something like largest volume ellipsoid or something like that. Okay, so that's an LP. And we just worked out this. Calculating the maximum volume ellipsoid in a set is also a tractable problem. And this is called the maximum volume ellipsoid center. So it's called XMVE. This is X Chebyshev. And you can think of lots of others. This one has a very important property. It's affine invariance. Now, affine invariance means if I transform the whole problem by, for example, scaling the coordinates, if I stretch it some way, that'll change radically the Chebyshev center. But it won't change the maximum volume ellipsoid thing because everything will transform by, in fact, the determinant of t, where t is the linear part of the transformation. So this is affine invariant. Now, as to which is better or which is not, it just means if someone's calculating a Chebyshev center, you should ask them the following question. I mean, just ask them, how well do you trust your choice of coordinates? Have you scaled everything properly? This kind of thing. Is it true that x3 being on the order of 1 is about the same as x2 being on the order of 1? If they don't immediately answer that question with, oh yes, I've been very careful to scale everything here very carefully, so they're on the same order. If they don't immediately answer it that way, then you need to poke them and bug them and say you better check your scaling because it matters here. Here it doesn't matter at all. So it's affine invariant. So, okay. Another center is the so-called analytic center of a set of inequalities. Say, that's a typo. So this we're going to look at in great detail in 2 weeks from now. So when we actually talk about interior point methods and how do you solve all these problems. So we'll save that for then mostly. But it's this. what you do is you set up a problem. You have some equality constraints and you have some inequalities, and these don't really matter. You want the margin here is actually minus fi of x. So for example, if minus fi of x is 0, you'd say it's tight. Minus fi of x is 1 would say you'd have a slack or a margin of 1. And you kind of want to minimize the margin. And there's lots of ways you could do it. You could minimize the maximum margin. Maximize the minimum margin. But an interesting one is to maximize the product of the margins, which is the same as minimizing the negative sum of the logs of the margins. Okay, so that's another method. It sounds odd, but we will get to what it means later. We'll also see that although this looks rather complicated, it turns out it's shockingly low complexity. So we're talking 15 lines. Indeed, 15 lines that you will write at some soon. So, and it turns out here, by the way, in this case, there's also an ellipsoid inequality. About if you calculate this, you'll get an inner and outer ellipsoid. Yeah.
You solved the maximum volume ellipsoid problem.
Yeah.
How would you extract that center?
Oh, that's part of the data. I mean, you get. I forget how we parameterize it with B and D, or does anyone remember? Yeah. So that's easy. Yeah, you might have to do some calculations, but whatever it is, it's very, very straightforward. You transform it. I don't know where it was. Forget it. It's easy enough. It's a quick linear algebra calculation to get the center. Okay, so here's an example. This will be important later, so I don't mind going over it. Also, by the way, just the idea of an analytic center is something that in many applications should be propagated. You'll see lots about this in the next 2-3 weeks and related problems, but it's something that should just be propagated. Because anytime you find a problem where someone says, here are my specifications, here are my inequalities, pick me a point in them. And you say, really, any point? Like, what if I picked a point just barely in them? And they go, no, if you're going to pick a point in them, you might as well get one that kind of satisfies a bunch of them, or something like that. Analytic center is actually probably a good choice. And it actually comes up in lots and lots of, already comes up in things like maximum entropy estimation, and we'll see all those connections. Okay. So for a set of linear inequalities, we have a polyhedron, and these are the level curves of this. This is a so-called log barrier function for this thing, for this set. And you can see the level curves here. When you get really high curves, they kind of hug the shape of the polyhedron. At the minimum, here, that's a smooth convex function. So it's got a minimizer here. That's the analytic center. And the analytic center here, this is a smooth convex function. Near that minimum, this thing looks like a quadratic, period. Therefore, the level sets near the analytic center are ellipsoids. That ellipsoid is a pretty good approximator of the shape of this set. Okay? And indeed, there's a bound. Now, the bound is interesting. The bound, so you can puff it up by, well, a factor of m. That would be m squared. You can puff up the ellipsoid by a factor of m. But m is not the space dimension. It's the number of inequalities. So it's a worse. It's worse than the maximum volume ellipsoid or Lohner-John ellipsoid. So that's it. Well, we'll get to these ideas later. Okay. Let's look at another topic is the idea of discrimination, classification. It's got lots of names. And let's see how that works. So you want to separate. Here I have a bunch of points in Rn, and they're labeled. They have binary labels, or they're classified. They have binary classification. So I could think of it this way. These, I'm labeling them actually by the symbol. So X is one set, Y is another. This could be, a bunch of vectors of something where there actually was something present. And this could be a bunch of vectors where something was not present or something like that. But I know which is which here. I'm told which are which. And what I want to do is this. The oldest problem, and by the way, linear discrimination, this goes back easily to MIT in the 40s and probably earlier than that. So this has a long, long history, the idea of linear discrimination. So what you really would like, what you want to do is find out, is there a separating hyperplane for this data set? Very basic question. And if there is, it means, is the following set of inequalities feasible. That the x's lie on one side and the y's on the other. Now the variables here are a and b. Now there is one difference here. These inequalities are strict, okay? And in fact, we haven't dealt with strict inequalities yet, but we're going to now, and you're going to see a trick. By the way, let's work out the non-strict classification. Let's have that discussion right now. Under what circumstances can two sets of points in Rn be non-strictly separated? That means when does there exist an A and B for which, let's say, this is true? When? Always. And by what choice of A and B?
0.
What if they're, yeah, 0, 0. So I choose A equals 0, B equals 0, and this always works. Even if the points are all like messed up in, next to each other. In fact, what if they're identical? So that's why it doesn't make any sense to look at that problem. We have to look at the strict problem. Now we haven't looked at strict inequalities yet. So now I'll just tell you that the trick is very, very simple here. These inequalities, take a look at them. They are equivalent to a set of non-strict inequalities. They are equivalent to these, where I put a 1 and a -1 there. Okay? This is this trick, you will be carrying out this trick. You need to get it. Okay? Here's the argument. Watch this. If there existed any A and B where strict inequality held here and strict inequality held here, this is homogeneous in A and B. So is that. So suppose the A and B you give me that satisfies this has this. These are 1e minus 5, and these are -1e minus 5. I can multiply those A and B by 10 to the 5 and make the gap plus and minus 1. Okay, so then I can make it this way. Now conversely, if A and B satisfies these inequalities, obviously these imply that. So that's how you do this. So these are tricky, and you have to, and if you do these wrong or casually or just, normally, there's a lot of cases when a strict inequality you can just replace it with a non-strict inequality, and no one's going to get hurt. In fact, the original one didn't even make any sense. Here's an example. If someone says to you, I'm designing a circuit, and the power can't be more than 50 milliwatts, and you say, really? And then later you get a design document, and it says, as item number 1, P is less than 50 milliwatts, like that. It probably means whoever made this up hasn't thought very much or whatever, because you'd say, really? Could it be exactly 50 milliwatts? Anyway, this is silly. But they probably meant that, and there's no engineering difference between the two. Makes absolutely no sense, because you'll judge this by spice or something like that, and your error will be, it won't be that good anyway. Anyway, if you manufacture it, it's going to vary plus or minus several percent anyway. Just change the room temperature and it's going to change. Okay, so the point is, that's a case where the distinction between strict and non-strict is totally irrelevant. This is just due to the ignorance of the person who wrote the specifications. They didn't know there was a difference. Okay, so that's one. This is not one of those cases, because if you just casually make these non-strict here, the answer is 0. Okay? If you're using some tool to get the answer, you will not get an answer. Because if you give a problem to a solver like that, it'll be very, very happy to give you the answer. Okay? And it won't be the one you want. Okay? So this is a case. So there are cases where the strict versus non-strict inequalities actually matter in practice. They matter a great deal. I mean, also, this all matters conceptually, too. I mean, so you should not confuse the two ever, frankly, but okay. Now, to check if there's a set, if there is a separating hyperplane, is actually just a set of linear inequalities. That's this, okay? In A and B. So for us, it's an LP feasibility problem. There's nothing more to say, period. Okay? Oh, well, we will say more. We'll say it next week, but that's it. Let me just mention something about what you might use this for. You might use it this way. You might actually take a whole bunch of snapshots of stuff where something actually happened, like a target was present or something, or a disease was present or something. These could be gene expression data. This could be the gene expression data, giant piles of gene expression data where a disease was not present. Okay? These, of course, would have a dimension. These x's could easily be 1,000,000 dimensional. For example, something like that. Okay? Then what you want, I mean, then suppose there were a separating hyperplane. There wouldn't be. But let's imagine that there were one. Okay, if there were a separating hyperplane, you could actually now do something quite interesting. Somebody shows up, you do the gene expression array, you get the data, and you plug it in, and this number here will either be positive or it'll be negative. If it's -3, you might guess with some confidence, I mean, depending on whether you believe any of this, that some disease is present. By the way, if it comes out about 0, that's a good time to say, we don't know. So we'll get to this shades business, but that's the kind of thing you would use a separating hyperplane for. So would be basically to do predictions of new points and where you don't know which of the two outcomes actually will happen. You want to predict. Okay, so we'll quit here.